This is the screencast for section 3.5, example 7. We're going to look at Newton's law of cooling. An object that has been heated will cool to the temperature of the medium in which it's placed. So if it's placed in the air, that's the medium. If it's placed in water, that'll be the medium. The temperature T of the object at time t can be modeled by, so the temperature capital T of time little t equals T sub m, and that's the temperature of the surrounding medium, so the air's temperature or the water's temperature, plus, and then in parentheses, T sub 0 is the initial temperature, minus, there's your temperature of your medium again, e to the negative k is just some constant depending on the situation, and then times time. So in example 7, a hard-boiled egg at temperature 96 degrees Celsius is, so 96 degrees, that's going to be the initial temperature of the egg. So this is T sub 0. Is placed in 16 degrees Celsius water to cool. Oh, so that's T sub m. Our medium in this case is water, and that's the temperature of our water. 4 minutes later, so at time t equals 4, I guess, the temperature of the egg is 45 degrees Celsius. So that looks like a point I can use, 4, 45, an input and an output. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So I'm looking for a final capital T value of 20. So let's plug some stuff in. Capital T of T equals, okay, the temperature of our medium we said was 16, plus the initial temperature of our egg was 96, minus the temperature of the medium, which is 16, e to the negative k, which we don't know k yet, times t. So I can do 96 minus 16, that's 80, no problem. But now I still have k that I don't have a number for. So I'm going to use this point that they said in the situation, 4, 45, to help me solve for k. So I'm going to plug in 45 for the output temperature, and 4 for the time. Now k is in the exponent, and in order to solve for exponents I'm going to have to use logs, so I know that logs will be a part of this. I'm going to subtract 16 from both sides, then divide by 80, and here's where logs come into play. I'm going to take the, either can take the natural log of both sides or just change this to log form, and I'm going to use base e because the base of my exponent is e. So I'm going to choose to change this to log form. So I'm going to use log base e because that's the base of my exponent. So I'm going to do natural log of, let's see, logs find exponents. So the exponent is going to go after the equal sign. And then I'm going to take the log of 29 over 80. Divide both sides by negative 4. And I get that, let's see, the natural log of 29 over 80 all over negative 4 equals k. Now, I know you could put that in your calculator and find out what the decimal is, but I want to make sure that we don't use the rounded value until ever. We actually have to use the actual value. So I'm going to set the equation back up as now I found what k is. So now I have T of T equals the initial temperature of the medium, which was 16, plus the initial temperature of the egg. So I still am using 80 e to the negative, and then k we found, but I'm going to just write k. The reader of my problem knows that k is over here. They can look at its value if they need to, but I'm not going to use that until the very end. K times T. It says use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So I'm looking for an output temperature of 20 degrees Celsius. So I plug in 20 for y, subtract 16 from both sides, divide both sides by 80, change that to log form, so log base e of 120 equals, and then logs find exponents, so that exponent is going to be on the other side. Divide both sides by negative k. Remember, k has a value, it's over here, but it has a value, so I'm going to divide by negative k, and I can find how much time it's going to take by plugging this into my calculator. so negative, and then my k value finally will be the natural log of 29 over 80 all over negative 4. So I'm going to plug that mess into my calculator. So 11.81 minutes. The now try problem number 49 is the same setup. A cup of coffee this time has cooled from 92 degrees Celsius to 50 degrees Celsius after 12 minutes in a room, so now we're talking about an air as our medium, at 22 degrees Celsius. How long will the cup take to cool to 30 degrees Celsius? So let's see. T of T is going to equal the temperature of my medium. The room is 22 degrees Celsius, plus the initial temperature was 92 degrees Celsius of the coffee, minus the temperature of the medium, so that would be 22. E to the negative, now we're going to be solving for K this first round, times T. And the point they gave me in here was that after 12 minutes, the cup of coffee was 50 degrees Celsius. So 50 equals 22 plus 70 e to the negative kt. So I'm going to use the same method I used in example 1 to solve for k. And now that I've solved for k, I can plug in my final temperature that I'm looking for the time to get there. So 30 degrees Celsius I'll plug in for t. And then I can solve for k, again isolating e to the negative 12k and then changing to log form. And I get that t equals 28.41 minutes after taking the log expression I found and plugging in the k value from earlier.